Okay, so the difference here is that with the residualized gain model, the outcome here is post-test. So the post-test, again, so the post-test and pre-test both have distributions that range from 0 letters that you know to 26 letters that you know. So the more letters you know at pre-test, the more letters we think you're going to know at post-test. They're positively associated. When we have change as the outcome, which is how we've computed it as post-test minus pre-test, when change is the outcome, now the pre-test is negatively associated with change. And that's because our change value ranges from some negative number to some positive number, because some kids probably lost letters over the year, some kids gained letters over the year. And so the more letters you knew to begin with, the fewer letters you gained, which you all were saying is probably because if you know all the letters, you don't have any more letters to learn.
The other question that we were talking about in our group, and perhaps it's related to this, is why the R squared tends to be larger in the residualized model compared to the simple gains.
Believe it or not, those two answers are extremely related. So R squared is the variance that's been explained. And you explain variance with larger B or beta weights. Well, we don't have beta weights here, but larger effect sizes, essentially, meaning you've decreased the variance by a lot more. So we can think about decreasing variance by looking at our f-tests. So here, with pretest in the model, look at our f-test, 2.1. This is the amount of error explained, right? The mean squared error here is how much error we've explained in the model. So let's go up to the first one where the outcome, instead of being this change variable we created, the outcome is post-test. So when the outcome is post-test, then here, pre-letter knowledge, look at the size of this F. 111. So we're explaining a lot more of the error. We're explaining a lot more of what's going on when we have the post-test as the outcome. That's also reflected here by the pre-test having a B weight of 0.878, whereas before it was like negative 0.12 or something. So in that case, so it's the same idea basically. It's the reason why our R squared is higher here is because pre-test is more highly correlated. Remember, correlation is a huge component of what goes into this B weight and what goes into variance explained and how much of the error we're explaining. So we have with more variance explained here and with a higher correlation between pre-test and post-test, we have a higher R squared and we have a more variance explained overall. Does that make sense? Ish. Okay, so now let's contrast what we just talked about there with the information we get from the repeated measures ANOVA. So within this repeated measures ANOVA, we're going to get within subjects contrasts. So within subjects means things that change within a person. So that was our time variable. And then we have between subjects contrasts, and that's primarily our treatment, whether you were in the treatment group or the control group. So here, in the within subjects contrasts, we get an estimate for whether time has decreased our error, the measurement occasion, and it has, and for whether the interaction between time and our treatment group has decreased our error, and it has. And then here we have the test of between subjects effects, and here you get your first direct main effect test of the treatment. But key here is that what you're testing with this test of between subjects effects is not whether the treatment is effective at reducing change, the variance in change. You're testing whether on average across all measurement occasions, that's both time 1 and time 2, whether on average, knowing whether someone was in the treatment condition helped reduce the error in your model. Now, there's no reason to suspect that knowing which group you were in at pretest shouldn't help us. Their kids should not be different at pretest because we haven't done anything to them yet. We hope that they're different at post-test, but as we talked about before with main effects versus interactions, if you have an interactive effect where something matters for one part of your effect and not the other, it might minimize your effect, which is what's happening here. So far, this is the closest thing we have to a test of whether the treatment group and time are both related to our outcome. And we have some sort of vague sense that something's happening because there's a significant F-test. But exactly where that significance happens, we don't really know. Usually we get some clarification from our parameter estimates. So that would be here. But within the parameter estimates, all that we get is an estimate of the intercept, how many letters kids know at pretest, and then a test of whether there's a difference between the treatment group and control group at pretest. And then we get the mean at post-test and a test of whether they're significantly different from one another at post-test. So here we see, no, there's no difference at pretest. No, there's no difference at post-test. But we haven't actually tested the gain. We haven't tested it either way. We haven't tested it using controlling for time 1, and we haven't tested it in terms of actually measuring gain. And so when I say I don't really love repeated measures ANOVAs, this is why, is because most of the time in the kind of work we do over here in education science, what we care about is, have some kids gained more than other kids? Or some people gained more than other people? And this doesn't give us a nice, clear, direct test of that within the parameter estimates. Not in the same way that we can get from the other 3 ways that we talked about above. Okay, I'm opening the floor to other things. Go ahead, Sarah.
Is there a specific time or type of question then that the repeated measures would be a better choice?
Yeah, so repeated measures is really good if you have 2, 3, 4 time points and you expect that there will be systematic change across those time points. So you want to test the main effect of whether time is happening, whether time is related to your outcome. So if that really is your question, is time related to your outcome? This is a great way to test that. If you don't care about the interactions between your within subjects and between subjects, this is a fine way to look at things. The parameter estimates here they only focus on one level at a time. They won't give you across multiple. So I'm working with someone who is doing an intervention with a group, with some families, and she's helping them learn stress reduction techniques. And it's a pilot study, so it's a really early phase study. And what she's doing is she's intervening with a small group of people trying to reduce their stress over time. So it's a group of people who she thinks will not reduce their stress otherwise, but that probably by introducing this technique, she expects that stress will be reduced over time. So when she has 5 possible assessment points, 1 each week, something like that. She's working with them for 5 weeks. So she's going to look at a pre-test and then a post-test after 1 week, a post-test after 2 weeks, etc. And so her primary research question is stress going down? And so she's using a repeated measures ANOVA to test whether stress is decreasing over time, because that is actually what she cares about and how she's going to demonstrate that her intervention has some promise. There's no between subjects effects in there. It's all within subjects. The key questions are within subjects effects. These are also really good if you have, if you're doing lab experiments. We don't tend to do that kind of work in education, but sometimes it comes up where you do something like, I want you to do 10 trials like in this circumstance and then do 10 more trials in this other circumstance. So try to remember something 10 times and then try to remember something while I'm throwing balls at you and you have to try to duck out of the way and I'm making it more difficult. In that case, you would expect to have a main effect of time based on a within subject's condition. You may not have a main effect of time because you don't expect necessarily that you get better or worse over time, but you would have a main effect of whether or not I'm chucking stuff at you. Yes or no. So that's a within subjects factor. Okay, other things about these.
Our group also had a question about causation. I think that's one of the later questions. Like, how do we decide then in that case if there's a cause or if it passes the causation test?
Yeah, that's a great question. So we talked a little bit about this at the beginning of last week's class, where causality is mostly established by use of the research design and not the analytic method. So in this case, in the research design, we've set it up so that we have randomly assigned people to either be in the treatment group or the control group. And through that random assignment, we have equated these two groups on expectation, and we assume that whatever is affecting one is affecting the other in the same way. And so any differences between these two groups are caused by the fact that we randomly assigned them to this particular group. Because that's what we've changed. If we're in a situation where you have looked only at the correlations between groups, you don't have any causal method, you haven't implemented a research design on top of it that involves some sort of treatment effect, then you can't necessarily infer cause unless you do several other things, which are a little bit beyond the scope of this class.
What about in terms of accounting for covariates? Do we say that's also part of the research design, or is that part of the analytics?
That's such a good question, and it's actually really complicated, but I'm going to give you a simple answer and tell you that there's lots of work on this subject. But the simple answer is that because we've randomly assigned people to groups, the effects of covariates shouldn't matter for our main effect of whether the treatment works.
Okay.
Because whatever it is, say income, distribution of income, because we've randomly assigned kids to groups in this experiment, that we expect that there should be a random distribution of income, that both groups should be equal on their income distribution. We should have about the same number of kids who are super poor and about the same number of kids who are super rich and the same number of kids who are in the middle within each group. And because of that, we don't need to necessarily control for that within this experimental design, where we just want to know, is the treatment effective?
Got it.
If you're working on, so we talked a lot about alternative explanations in the last class, and those are really mostly for when you have an all correlational design and have not implemented some sort of experiment. Now, the long answer is that sometimes those things can come into play if somehow through unhappy randomization you've ended up having completely unequal groups, then we may need to bring covariates back into the question. It also comes into play if you think maybe your treatment is more effective for some kids than others based on some sort of covariate. Then those variables can enter into the model as well, and you can start testing them that way. But for the base question of, did the treatment work in my randomized control trial, you do not need covariates. You make your life a lot harder at the beginning, but it's a lot easier at the end. Okay, so one thing that this raised within a group was, hey, if we have some sort of growth to plateau model here, that sounds kind of like a nonlinear relationship. So that was here within the relation of pretest with gain or pretest with posttest. So in this case, we might say, well, if you already know all of your letters, you can't actually gain a lot. So the relation between how many letters you know at the beginning and how much you grow might not be linear. It might depend on how many letters you knew at the beginning of the year. And so, just for fun, I would like to test that. So I'm going to pull open this and we'll walk through it together. Here's our data set. Here's our code. And what I'm going to do is create that new variable. Oh, I don't need to create a variable, do I? So to test whether is to test whether it's not linear with prelet. Then we're going to add prelet because that's our main effect. And then we also need to add the interaction term. So that's prelet times prelet. That's the quadratic effect, or prelet squared. And here's the main effect of prelet. I'm going to keep the treatment effect in the model. And now let's see what happens. Looks like it ran. We have two groups. We get the means of each group, the mean change for each group. Here's our type 3 sums of squared errors. Right here, we're learning that prelet within this model, once we've included the interaction, the quadratic term, is no longer reducing our variance. And the interactive term is also not decreasing a variance in the model. But let's look at the parameter estimates. In the parameter estimates, we see what? These look pretty similar to how they looked before. We have a significant effect of treatment. Here, though, what we see is that it's no longer associated, pre-letter is no longer associated with how much they changed. And the quadratic effect is very minimal. Interesting, though, this turned positive. So it tells me that there's it's still not significantly different from 0, so it's not a huge change. But that's interesting that once you've accounted for how it might change over itself, across the distribution of itself, you end up with a positive relation here. It's still 0. Interesting question. And now for fun, let's do it with post as well, and then we'll actually move on. So now for post letter, and we're controlling for pre-letter. So this is the residualized gain method. With this in the model, we end up with a similar story where pre-letter is associated, though this time. It's reducing our error. But the quadratic effect is not significantly contributing to decreasing the error in our model. That's playing out in a very similar way here. It's still a positive association. And then this quadratic effect is not significantly different from 0. So it's decreasing ever so slightly over a number of letters. So it may be a growth to plateau, but it's not a very steep one. So This is a really good example of the kind of thing that might have worked for the very last question on this assignment, which is, what does this raise for you? So for at least one person, this raised, is this just a quadratic relationship and we're not analyzing it correctly? And the answer in this case was no, but it could have been.